Lecture. Here we go, folks. We're getting into the spectroscopy. All right, so this is kind of going to be a little all over the place with respect to the chapter and section that we are in the book. The book kind of divvies up everything on spectroscopy in kind of a weird way. So that's why you see that it says select content from chapter 13 here. And so that's gonna happen with some of the other chapters. So I apologize for that. I'm gonna try to keep it as organized as I can. But I wanted to put together like a custom set of topics that I think fit nicely together. Okay. Excuse me. So the first thing I want to get into is a little bit of review. So hopefully this all looks familiar. I know we've talked about this in Chem 361, but also in your other classes. Okay. And so what I want to describe is simply the phenomenon of light passing through an absorbing sample and then going on and detecting that light. Okay. So let's label a few things here. So I0, this is what we call the incident radiation, and that could be ultraviolet, visible, infrared, right? So we're just going to say generically that this could be, any incident electromagnetic, let's put that qualifier in, EM radiation, okay? So when we have an absorbing sample, the intensity of this light will decay exponentially through the sample as it passes through, right? So if we imagine looking at this as a wave coming through, right, we will see this exponential decay of light intensity. And if the optical depth is sufficiently small enough, then light will make it out of the other side, okay? If the optical depth is sufficiently large, then that means all of that incident radiation has been absorbed and we won't detect any, okay? So this is why we typically look at low concentrations in spectroscopy so we can make sure all of our incident radiation comes through so that we can detect it. So, and often I draw a little profile of an eyeball right here to symbolize a detector, okay? So that is an exponential decay, right? So by definition, optical depth tau is given as the natural log of the ratio of the incident radiation to the transmitted radiation. Okay, so let's define that. So that's the transmitted EM radiation, defined by I. Okay, so it is an exponentially decaying function. So to me, it makes good sense to use the natural log. And of course, we could define the transmittance T as the ratio of the transmitted EM radiation over the incident radiation. And that will also have an exponential function. That transmittance can be written as the exponential of the negative optical depth. And of course, as you might imagine, if we supply, right, if we write that in, e to the negative natural log of I naught over I, then the e to the natural log cancels that out and the negative sign makes these flip, and that's where we get this to be I over I naught, okay? So why we use log base 10 for absorbance, I have no idea. Maybe just to confuse you poor students even more. But if I was writing the damn equations, I would have kept absorbance as a natural log relationship because it is a naturally exponentially decaying function. In any event, I don't write the rules. So absorbance by definition is given as log base 10 of IO over I. And of course, certainly we could say then A is the negative log of T, the transmittance. But what that means is if I want to relate absorbance to optical depth, then I have to change my base. And the way that I change my base is by taking the log base E of 10. And that will convert that log base 10 into a log base E. Okay? So we can use the Beer-Lambert law, Beer's law, as we know more colloquially. But the Beer-Lambert law can be written for optical depth or absorbance. So when it's optical depth, we typically will report we will typically report concentration there. Remember, in molecules per cubic centimeter. Okay, so our path length is always given in centimeters. And so what this means, this sigma, if you recall from Chem 361, this is called our absorption cross section. And that's given as centimeter square per molecule. And it's very much a cross section, the way that this is viewed. So in other words, a small cross section will lead to not very much light being absorbed, right? If I imagine now a wave coming in through here and I've got a small cross section, then I'm going to be able to transmit through the other side, okay? But as you might imagine, if we were to have a very large cross section, that large cross section we could really think of as like a sponge for all of our photons. A large cross-sectional absorption area will suck up all of those photons and none will be left to transmit. Okay? So that is the natural way of looking at Beer's law in the base E. Of course, the way that you've all been looking at Beer's law, which is the way we do it in chemistry, is the base 10 measurement, where now my concentration here is expressed in molarity, mole per liter. My path length is still given in centimeters, and now that means my absorptivity coefficient, so I'll just say, I'll write that as absorptivity coefficient. So that's going to have units of, it's got to be reverse concentration, liter over mole, and because the centimeter is there, centimeter. And now, of course, this quantity, the absorption coefficient, we know that we normally empirically determine that coefficient, right, by making standard curves and so on. But if we wanted to relate that absorptivity coefficient to the actual physical parameter, the cross section, then we'd have to consider this base E. Okay? And so if I do the algebra here, assuming that my concentrations are the same, right? We know that we have different concentration units, so there is going to be a factor of like Avogadro's number and the conversion of cubic centimeter to liter. So if we ignore those conversions, okay, then I can write that the cross section sigma, right, and I have to multiply natural log of 10 up there, and the natural log of 10 is 2.303. So I'll write that down, okay? So that means the absorption cross-section equals 2.303 times the molar absorptivity coefficient, assuming that you've also got equivalent units, right? So that 2.303 factor is just for the base E to base 10 conversion. Okay, so hopefully that was good review. And all forms of spectroscopy generally follow this mantra, okay? At least all transmission spectroscopy techniques. Not all spectroscopy techniques are transmission techniques, and we'll talk about those as well.